Hello, welcome to this session on wave equation and solution. So, in this session we are going to learn the formulation of the wave equation, the source free wave equation and how it is solved. So, let us write down the wave equation. I mean let us write down the Maxwell's equation in source free medium. So, curl of E is equal to minus z cap h and curl of h equal to y cap E. So, there are no sources in this equation. So, let us write let us call this equation 1. Now, in order to recast this equation in terms of either E or H, we need to drive out H from this equation or we need to drive out E from this equation. So, we need to perform the curl of this equation of the first of this equation and substitute from curl of H from the second equation to the first equation, okay, as simple as that. So, we perform curl E equal to minus z cap curl of H, and substituting from the second set of equation, which is the second of the equations, which is curl of H equal to y cap E, we get curl of H equal to y cap E. So, needless to say z cap is j omega mu and y cap is j omega epsilon, and y cap is sigma plus j omega epsilon. So, we can write k equal to root of minus z cap y, it is the wave number in the medium. So, if there is no conductor, if so it is a source free case, homogeneous medium without any conductor. So, y cap will be equal to j omega epsilon without any conductor. So, k is called the wave number in the medium. And therefore, we can write the previous equation as curl E minus k square E equal to 0. This is equation number 2. Similarly, in a similar fashion, we can find curl H equal to y cap minus z cap H, that is equal to k square H. So, we take the curl of the second equation and substitute for curl of E from the first equation to the second equation, as simple as that. So, we can write this equation in terms of curl H minus k square H equal to 0. So, this is equation number 3. Which is similar to equation number 2. in terms of magnetic field. Now, we also know that divergence of B, which is divergence of mu H, equal to 0. We already know that fact, that the magnetic flux forms closed loops, there are no magnetic sources. So, therefore, divergence H is 0. Therefore, divergence H is 0. We call this equation number 4. Also, divergence of D is divergence of epsilon E that is equal to q v, the charge enclosed, and that is equal to 0 because we are in a source free region. We are in a source free region. So, divergence of D is also 0 and divergence of E therefore is 0. We write that down, divergence of E is 0, that is equation 5. Now, we have from a vector identity grad square A is divergence. We have from a vector identity grad square A equal to grad of divergence A minus curl A. This is a vector identity true for any vector, and therefore, substituting the electric field for A, if I substitute the electric field for A, is grad square E is grad of divergence E minus curl E, and because of 5 where divergence of E is 0, this can be written in terms of minus curl E. That is from 5. Similarly, for the magnetic field, we have grad square H as minus curl H from 4. Hence, hence 2 and 3 can be written as minus grad square E minus k square E equal to 0, which will imply grad square E plus k square E is 0. and minus grad square h minus k square h is 0, which will mean grad square h plus k square h, which will imply grad square h plus k square h is 0. We call this equation 6 and we call this equation 7. So, these are the wave equations satisfied by the electric field and the magnetic field. The same wave equation is satisfied by the electric field and the magnetic field. This wave equation is also called the Helmholtz equation. So, these are these two equations. So, both electric and magnetic field satisfies the wave equation or the Helmholtz equation. So, both these equations can be succinctly or shortly written as grad square phi plus k square psi. Both these equations can be succinctly or shortly written as grad square psi plus k square psi equal to 0, where psi can be either E or H. So, as we said, if the medium is a perfect dielectric, y cap is j omega epsilon and z cap is j omega mu. Now, suppose the electric field, suppose the electric field possess only a x component. That is independent of x or y. It is dependent only on z. So, the electric field is x polarized, which is independent of x or y and dependent only on z. Therefore, we have d square E x d z square, because the other variation del square del x square or del square del y square will be 0. So, we only have d square E x d z square and the other field components are 0. So, there is only E x. So, plus k square E x equal to 0. So, as I said, two things need to be noted here, that there is no variation with respect to x or y, no variation of electric field with respect to x or y. And you have one polarization which is dependent only on z. Now, the solution to this equation is of the form E x e to the E x, the solution to this equation is of the form E x equal to E naught e to the power plus minus j k z. Let us call this equation number 10. So, this becomes equation number 11. Okay. The variation of the wave number, as I said, root of minus j omega epsilon j omega mu, that is minus z cap y cap, that is equal to omega root mu epsilon. That can be given the name 9. So, now let us consider the solution. Let us consider the solution. E x as E 0 e to the power minus j k z. So, this is a forward going wave. So, let us consider this solution. So, this is a forward going wave, we will see that later. Then curl of E will be equal to u x then the source free Maxwell's equation can be written minus z cap h equal to curl of E. With curl of E given by u x e y e z del del x del del y del del z E x 0 0. So, that will become, you see, u x, there is no component. With u y we will have del E x del z and with u z we have one component del E x del y, but there is no variation with respect to y. So, there will be no component E z. So, there will be no component along the z direction, there will be no component along the z direction. So, this can be written as E x minus j k u y because of this del del z in differentiation. So, e to the power minus j k z. So, minus j k is going to come out and then we are going to have e to the power minus j k z. So, that will be the same as E x. So, because of this differentiation the minus j k term is going to come out of the e to the power minus j k z. So, therefore, minus j omega mu h is equal to minus u y j k E x, that is from here. Therefore, H has only a y component, will be j k E x by j omega mu, cancel this. So, that will be equal to k by omega mu E x. So, now we come to the concept of wave impedance. So, eta, the wave impedance, is E x by h y, and that will be equal to omega mu by k, that is omega mu by omega root mu epsilon, that is root of mu by epsilon. It's 12. So, this wave impedance, what is the significance of this wave impedance? The significance particularly is that once we can calculate E x, once E x is calculated, we can find out H y, or if H y is calculated, we know E x. Now, you will see that this is free space, the wave impedance is uniquely defined. If the medium is a guided wave structure, the unique definition of wave impedance is going to slowly vanish. We will see that in the waveguide, the wave impedance cannot be uniquely defined, or the characteristic impedance cannot be uniquely defined. In hybrid guided wave structures, when you take the ratio between different transverse components, you are going to get different results. So, the concept of wave impedance or the concept of characteristic impedance in hybrid guided structures, where both the electric and magnetic field along the z direction exist simultaneously, okay, there the concept of wave impedance totally vanishes, or the characteristic impedance, it totally vanishes. Okay. So, in this case, this is called the wave impedance, and in vacuum eta is root of mu naught by epsilon naught, and if you substitute root of mu naught by epsilon naught, in vacuum eta is root of mu naught by epsilon naught. When I substitute for mu and epsilon in vacuum, and that is approximately equal to 377 ohm. So, now the concept of, just to clarify the concept of a forward going wave. So, let us suppose now the concept of a forward going wave, as we said. So, let us suppose E x 1 is E naught e to the power minus j k z. So, the corresponding instantaneous wave E in x 1 is root 2 E naught cos omega t minus k z. So, you see, for a constant phase point, as time increases, z will also increase. For a constant phase point, as time increases, the z will also increase in order to maintain constant phase. So, this is a forward going wave. So, the wave moves forward as time increases. Similarly, we have another wave E x 2 as E naught e to the power plus j k z. The corresponding instantaneous wave is E in x 2, which is root 2 E naught cos omega t plus k z. So, you see now in order to maintain constant phase for a constant phase point, as time increases z has to decrease. So, as time keeps on increasing, the wave moves backward. So, as time keeps on increasing, the wave moves backward. So, this represents a backward going wave. So, this represents a backward going wave. So, we discussed the wave equation and we took the representative example of a x polarized wave with which is independent of x or y variation, and we came also to the concept of characteristic impedance and the concepts of the forward going wave and the backward going wave as and the concepts of forward going wave and backward going waves and their representations. So, we will end the lecture here, we will continue with this.